All right, looks like we'll get started for this afternoon. Thank you guys for coming back for more pain and torture with Chris for the rest of the day. Administrative notes, you're supposed to turn off cell phones. I don't care, but it's on the note. And you're supposed to fill out evaluation forms. If you fill them out very badly for me, I won't have to do this again, so that'd be awesome. Thank you very much. Anyway, so this afternoon, two topics. We'll talk about debugging GPU programs, and my personal favorite, we'll talk more about optimization in lecture 4. This debugging lecture is not supposed to be like an intro to the tools. Nvidia has some really awesome debugging tools, and I don't think what I'm going to do here is going to do that justice. I want to make sure that you guys go to those appropriate sessions and things like that. I'm going to present debugging in a way that we see it from industry, sort of, to some extent. Like, as a user of the tools, what kind of issues do we run into, and how do we debug them? That being said, I'll still demo Insight and things like that, but I'll be doing it much more informally than a proper product presentation. So I'm not trying to represent or misrepresent NVIDIA anyway in their tools at all in that regard. So again, I kind of want to more share my experiences with you about debugging and things like that. I believe this lecture is actually going to be a little bit shorter. Probably will be the shortest of the 4 today, so hopefully they'll give us time for some questions and a good break. And then the last lecture's got more meat in it as well, so that's fine. And then you won't get as much of a snooze, after lunch snooze, as much as you'd like, but oh well, that's all right. Okay, debugging tools. There's lots of different ways we can debug. It's great. There's cuda-gdb. Parallel NSight, and Sebastian reminded me, you guys, probably some of you got the note on Friday, I think, that they've renamed Parallel NSight to just Insight for Visual Studio. So there's been a bit of a name change there. It's still Insight under the Visual Studio menu. I'll demo 2.2, the release candidate. I'll show you some things there. But again, I'm not trying to demo the product per se. I mean, I'm showing you some things, but again, you'll want to go to those sessions. Cuda-memcheck as well, we'll talk about, which is great for out-of-bounds checking. Just general debugging techniques outside of that. Most of this will be familiar to you guys just from writing software for so many years as well. So, okay, yeah, again, still about us for the new folks. Highlights, again, we do training, products, and services. If you guys are interested in getting up to speed or getting your code quickly ported to GPUs, yeah, come chat with us. Drop us a line. Let's see if there's a fit. We can do that very quickly for you guys. You want to learn more about it, you want to do some hands-on exercises, come to one of our training courses. It's much more interactive. It's over 4 days. We sit down with demo laptops and we go through. We get you to bring in your code if you can. We'll even take a look at that for you there during the training course. So lots of fun there. And we also do products, and the products we do are actually, that's my accountant, actually. And that's a researcher, and that's my marketing person. I really wanted to be in this picture, but I don't show up till like 11, and they had already done by then. So oil and gas, we do products for. It's reverse time migration, seismic type stuff. So those are standard off-the-shelf libraries that you can integrate. We also have an EM ones for finite difference time domain and things like that. We also have a biomedical image reconstruction type of product that you can use as well. And we also do the professional services, so we have courses in all of this. Similar to this, except, like I say, much more personal and hands-on, and it's a little bit more in-depth than what we're doing here. So, some common CUDA problems. What can you see when you're building in CUDA? If you built or had a chance to run CUDA, you'll see all sorts of fun things. In increasing likelihood, or decreasing likelihood, as in this is the top one is the most common, you're probably going to get wrong results, potentially. It can happen. Imagine that. We call it the dreaded unspecified launch failure. We see that too. You hang the machine. Display corruption, like I say, that's a lot of fun. If you're doing a really good job if you're corrupting your display, nice work. You can hang Linux. You can just hang the OS. And you can also introduce like complete spontaneous reboots, which are kind of difficult to debug because you're running to a point, but then the machine reboots. That one's tough to sort out. So you got to be careful there. By far, at least from our experience, and obviously you guys would have seen this in just regular C, the highest probability of error is going to be your out-of-bounds memory accesses. You're just writing an array out of bounds. It can cause anything. Perhaps worse, it doesn't cause anything at all. And then you get the joy of sometimes it works and sometimes it doesn't. and sometimes synchronization errors or race conditions. You might see this more when you're working, say, with streams potentially as well. You might run into a bit more race conditions. Those ones are nasty to deal with. We're trying to solve a multi-GPU bug back in the office today, at least. I hope they're working on that, because that's my product, so they better be working on that today back in the office. And we're trying to resolve, some sort of, it's writing before it's reading or something like that, or maybe the other way around. But whatever, it's not good. If you're in Linux, you probably don't want to be running X on the same display, running X on the same GPU as your CUDA application. CUDA does offer memory protection, but sometimes the current drivers will allow you to corrupt that. One of your best options, and you'll kind of see this when I work with Insight, is that if you can SSH or do a console in, that really helps the debugging process, because then you're not running your graphics display on the same GPU that's doing the computation. That's where you start to run into issues, and it can be a little bit of a problem. So unload, reload the Nvidia module if your kernel crashes or fails to launch. For Windows developers, originally this slide was written by a Linux guy, and he wrote, "Reboot, were you expecting something different?" But I think that's pretty harsh, and it's not that bad. But anyway, he wrote that. But we've changed it since. And Microsoft, they make a good tool, so I have no problems there. But but that being said, you can corrupt the display or the driver to a point where it is actually worth rebooting the machine to kind of have a fresh install there. All right. So debugging tools and techniques. cuda-gdb, if you're in Linux, works pretty well. Again, it's not Parallel NSight. It's Insight for Visual Studio now. And cuda-memcheck are useful tools. Obviously, code reduction, isolation, data examination, assert, and printf, and we'll talk about some of those going forward. If you're using cuda-gdb, this actually debugs the code running right on the GPU. The issue is you'll actually potentially need to run it just without the display on it. The GPU doesn't do so well if you break, like you do a breakpoint when it's trying to update the graphics. That's not so good, right? Because that's actually stalling the graphics. So you need to be running without X11, and same thing in Mac OS. And you can remote in. You'll want to compile with these flags right here when you compile with NVCC, which is the compiler for Nvidia. If you compile with those flags, that keeps debugging information, and the new cuda-gdb is going to support Kepler. You can do print just like you would with GDB. I have to admit, I don't use a lot of GDB, but it tells you all sorts of good information about what thread you're on, the information that's connected to each thread, your index, where you're running, what warp you're in, and it'll give you some information on the devices as well that you have there. You can switch to a specific block or thread. So again, we've launched with multiple blocks and multiple threads. You probably don't necessarily always want to debug 0, 0, the 0th thread of the 0th block. So you can switch blocks and basically switch scopes and do those kind of things. Scope shadowing not supported, so you can't, if you have the same variable name in multiple scope, like a global and local, it doesn't support that. Device memory is not visible outside of the kernel, so if you're debugging in the host stuff, you won't be able to see the device. Malloc host, we didn't really talk about this yet. It's pinned memory, page lock memory. You can't see that in the debugger. And if you kind of step, again, after stepping out of a kernel, you sometimes get undefined behavior. So there's a few limitations that we've seen there. Windows side, again, this is no longer called Parallel NSight. It works with 2008 and 2010. You won't be able to use XP. So if you have XP, you got to get Windows 7 at least, or some variant of server or something like that. It doesn't work in XP. It's a pretty slick tool, actually. It debugs, obviously, CUDA. It also does OpenGL. And again, by all means, I don't want you to say this slide is all it can do. There's lots of phenomenal stuff, and I refer you to the other sessions for that. It does do some memory checking stuff out of bounds as well. And again, you can switch threads and inspect memory and all that stuff. So it's all available from the Nvidia website as well. Some new features in Insight 2.2. One thing that's neat, and I haven't had a chance to try this myself, is that it should be able to work on a single GPU system. We're actually pretty excited about this because normally you can't have graphics being driven by a display when you're halting it. So we're actually pretty excited to see how that works. like I say, my laptop actually has, it's an Optimus chip, so it's actually having the Intel drive the display, so we can run NSight on it because the CUDA part's running on the Nvidia side, which isn't going to be halted. Or, I mean, it will be halted, but it won't halt the display, so there's no issues there. Supports the new Kepler architecture and, of course, CUDA support. PTX, that's the assembly level parallel thread execution. It's an assembly level of CUDA, so you can do debugging at that layer too, although I haven't done much with that either. You can set conditional breakpoints. You'll typically want to break, but not quite the same equals operation. You want to specify the thread and block index using this notation, which should stop this on thread index 17. Because again, remember you have thousands of threads, so the breakpoint's going to be tripped, but which thread is it? NSight will tell you, but if you want to stop it on a specific thread, you can do things like that. Cuda-memcheck, it's a standalone utility. This one's actually kind of useful. It'll detect if you are out of bounds. So we'll do that. We'll do a little demo with that, and we'll see that we're out of bounds. It'll also show you if you've leaked any memory, which is kind of cool too. So if you've got any leaks, your fail to free called CUDA free, we'll see that happen. If you actually have the -G compiled into it, it should report the line that's actually executing it. But more importantly, it tells you which thread is actually doing the out-of-bounds access, so that's good. So as an memcheck here, this is an example, although we'll do, like I say, we'll do one. It's showing that there was an invalid size 4, so it's writing a float out of bounds with this thread. The memory address isn't so meaningful, but that thread is writing out of bounds, for example, on line 5 and then line 8. One thing, and you've probably seen this if you've done multi-threading programming, sometimes if you debug or you insert print statements, it changes the order of execution. And when that happens, what may have been a race condition that caused a failure before all of a sudden works. And those ones are painful to sort out. It's just the nature of debugging. Obviously, also have a large problem size. It can take a long time to run, which is a little bit problematic. So, I mean, some just general suggestions, at least for what we do in CUDA, is we decompose our large kernels into much smaller device functions. We'll often put global wrappers around them and have unit tests attached to them, so that way you can validate that your device functions are behaving as expected, and testing the kernel in small chunks to isolate. Just shrink it as much as you can until you remove the potential issue. Watch your memory accesses, remove them, replace it with a constant, and find the minimum code, obviously, that reproduces the problem. There's some interesting things that can happen. So yeah, if tools aren't available, write patterns to memory too as well. That's also, we find that useful as well. One thing that's interesting too that you have to be a little bit careful of when you're doing your debugging is if you remove too much code, the compiler is very intelligent, and it will start to figure out that you're not actually, or that segment of code isn't necessarily doing anything. It's not being used, and it will optimize it out of your kernel. So you do have to make sure that you're still reading and writing the data, because if it determines that a variable goes nowhere, it won't actually include that in the code. So all of a sudden, you may have eliminated that section that may be problematic, but it's just being compiled out. It's not necessarily resident in the code. So because the compiler is very aggressive about optimization and does a very good job of dead code analysis. So yeah, you got to be a little bit creative there. So yeah, using test input patterns is always a good one. I haven't had too much experience with assert. It's new to CUDA 4.1, and you can call assert, and it'll print a message to tell you that a condition has failed. It's intended for debugging. You can disable it at compile time by defining this preprocessor macro to including assert .h around each call to assert. I do not believe it automatically gets compiled out, say, in release mode, for example. So you have to define that macro for now. Printf, this one's interesting, and when you're using printf the first time, you might run into this issue. You need a Fermi device or higher to do it, a 2.0 or higher. If you don't have a Fermi device, printf isn't supported. So what'll happen, though, is the default, and maybe today I'll try to show, not today, in this session, I'll try to show you the compile options, and if I forget, somebody just remind me. In fact, you'll actually see that the default is it's going to compile for SM10. What that stands for is Streaming Multiprocessor Compute Capable 1.0. So you can change the level by putting in an SM20, and it will compile for Streaming Multiprocessor 2.0 there. Then printf will be allowed. Otherwise, you'll get an error saying printf is not supported for devices of compute capability 1.0. So same thing with double precision, for example. You'll want to specify SM20. Otherwise, you'll get either a warning or an error message saying those features aren't supported. So if you are compiling for specific features, you'll need to make sure these are in your compile options, and printf is one of those examples. You'll also need to call the device synchronize or stream synchronize to flush the buffer to output. It actually records the buffer on the card, and then it dumps it to the host when you make this call. So of course, another nice thing is you just call printf in your kernel. Well, it'll print, if you launched it with 10,000 threads, it'll print 10,000 times. There's no filter, right? So you're going to probably want to put an if statement around that if you only want to see certain threads being used. Otherwise, you'll get 10,000 outputs when maybe that wasn't your intent. Okay, so I'm kind of leaving the tools a little bit, and I'm kind of moving more into the accuracy of GPUs and just some things that you can expect to see as you do GPU computing. The CPU and GPU aren't necessarily going to produce the same result. You might be like, well, Chris, math is math, right? Like, how can it be different? And we'll talk a little bit about that in these slides. And it is interesting because this is very challenging to debug as a programmer or as an engineer. How do you determine if it's just numerical precision or if it's actually an error in your code? There's a lot of different variables, compilers, optimization settings. Are you using SSE with Intel or are you not? Intel uses extended register precision, right? The GPU doesn't necessarily do that. So yeah, you've got floating point implementation differences as well. So just as a review, again, or you guys again probably know this, floating point is commutative. You can add them in either order, but it isn't associative, and that's nor distributive, because there will be intermediate rounding of results. So yeah, A plus B plus C isn't necessarily A plus B plus C. What? Yeah, okay, you guys understand what I'm saying. So the order of operation changes numerical results. Compilers as well and optimization settings may change the order, and also if it's a parallel or serial algorithm. I'm not going to go through this too much because I think it's pretty boring, but maybe you guys probably already know this anyway, but they basically represent a floating point number as a series of bits which then gets mapped to a floating point value. So you have this mostly for your reference. And same thing with double precision. So the first number is a single precision, 32-bit. And then the second number in the brackets would represent the 64-bit representation. So an example of that is obviously there's finite precision. 2/3 gets rounded in floating point representation. This eventually has to get rounded. Has to be rounded, sorry. So this example here shows it's setting A, B, and C, and it's scaling by some amount. And it's showing that the addition, the order doesn't matter. The reason is because this is showing how it works if you had infinite precision. But the next slide shows that if you round it, depending on when you do the rounding, you can see the last two lines show a difference in the last bit is basically what's happening. So there ends up being a slight difference in the value, and the order of operations will have an effect on the results. That being said, the Nvidia GPU does support the IEEE 754 standard. I noticed when I was looking at the sessions, there's actually a talk on that, and later this week, I think, and the details of what it supports, which might be kind of interesting. But just from my practical experience, sometimes we match to the decimal, like absolutely match perfectly with what the CPU does. Sometimes we don't. It's a little bit off. I notice with floating point, we see it a little bit more variance than we do with double precision. As Fermi has come out in later revisions, that gap has closed a little bit. So it's up to you guys to decide, is it good enough or is it not accurate enough for what I need to do? And again, that's not a question I can answer for you unless I get to look at your code. All right. So some more floating point differences. Oh, I shouldn't say AMD there. NVIDIA GPUs implement a fuse, multiply, and add in single precision. It's performed in a single instruction, and because of that, the multiplication is truncated. And most CPUs don't have an FMA type thing. So because of that, that can be some numerical differences as well. And again, yeah, sometimes the GPU doesn't necessarily support this, depending on the vintage that you have. There's also something called denormals, and it's how floating point is handled close to zero. the CPU may or may not be set to flush these to 0. So when you get values that are very, very low, they have a special mode to handle denormals. And Nvidia handles this in hardware, and it's actually very fast. It's good. The CPU is particularly slow, actually, at it. But again, if it's just being flushed to 0 versus actually doing the computation, that's going to affect your results as well. So yeah, again, like I say, a little bit of a short lecture, but we'll get a look at the demo after this. So yeah, you've got a few things to do this. Debuggers, GPU debugging will let you kind of bring some traditional techniques to the GPU. You can expect some numerical differences on your code, and some are due to floating point implementation. Sometimes it's due to order of operations and things like that. So, all right. Okay, so we'll do the demo now. And I don't think this is, yeah, this one isn't a volunteer one. I'll just kind of walk us through this one. All right. Okay, let me make this a little bit bigger for us again. Okay, so the idea here is that we're going to add 2 elements the size of 1,000. Again, we've allocated the data. We've allocated it on the host. And then we're just going to add it. So it's actually going to be a pattern that we can recognize in memory and stuff like that. So it's going to be 42 plus the index. So incrementing it just by a value of 1. Copy it to the device. Excuse me, launch the kernel. I do notice this is the correct order, so that's good. We memcopy it back, and then we free up the host data. So, all right, let's see if I can build this guy here. And I'm assuming I will not get an arrays match when I do this because there's supposed to be an error or something in this code. So let's see. Let's bring up the output window, make sure that works. If I build it, great. Okay, so I'm going to debug. Arrays do not match. Okay, so we'll have to fix that. So I'm going to try to launch the NSight monitor. The first thing I need to do when I do this is sorry, I want to launch NSight, but to do that I actually need to launch the monitor. Now, you'll notice it asks me to be an admin to do this. Typically, I think if you're in, say, a corporate or restrictive IT environment, what you would probably, I think this thing should appear here, my little icon thing. Oh, yeah. No, I'm not going to allow access. There it is, right there. So it's monitoring it. Typically what you would do is, let's say you had your laptop and you were debugging. You might, for example, remotely log into a machine that has this running on it already. So it might be like a server in your server room that your admin has set up, and it's got Parallel NSight, and then you would connect to it. I've got it running on the machine, so I'm just going to connect locally. It's just going to be like direct local connection, but you can connect it across a network, and that's how you can avoid the whole administrator thing. Okay, I had to close the project because I wanted to open it fresh. But that might be redundant. Okay, so then I'm going to start my NSight debugger. Okay, so a couple things that are kind of interesting that we see here too. Let's say you were to click Start CUDA Debugging. It won't force a rebuild. You know how when you click Debug, it'll detect if it's out of date. If you actually run it just like this, it won't actually detect that you need to do a rebuild. So it could actually run an old executable. So before you do this, you want to make sure that the image is up to date. Before I start the debugging, let's see what other things I have in this. So I've got some system info. So the other thing you'll notice here too is it's asking me if I want to connect unsecurely to the Parallel NSight monitor. You can establish a secure connection, and again, I refer you to the documentation for that. I don't want to take too much there. So it's actually gonna retrieve the information from my GPU. You can see in the lower right-hand corner, I connected and disconnected there. So it tells me that I have this processor with whatever frequency. My operating system. If I jump down to GPU devices, it tells me that I have a Quadro NVS 4200M on this machine. I've got this driver installed. It tells me I'm 2.1. I only have one streaming multiprocessor, it tells me. That's interesting. Buffer bandwidth, the RAM type of this. If you were to have Tesla, for example, it would be GDDR instead of DDR. CUDA devices. This gives you all the, what am I trying to say, maximum specifications. So it'll tell me 2.1, but it'll also tell me, for example, my maximum block sizes that you saw in Lecture 1. So that's kind of handy. So you don't necessarily have to go to the programmer's guide. You can just fire this up and take a look at your maxes and things like that here. So that's kind of cool. So I didn't even run it per se. I was just checking my checking that. Now these guys should probably be grayed out until I run it. So I'm going to start CUDA debugging. Obscurely. Ooh, I have a watch window. Okay, so first thing, it didn't like the driver version. That's because I'm using a developer release. Obviously, when the full release is out, I'm pretty confident that issue will be corrected. So that's why it's complaining about the driver version. Okay, so a couple things. So it's actually broke inside the kernel. Actually, I'll just close this up. Looks like it sort of remembered some of this stuff, so we'll try to start from scratch. The first thing I can do is inside a normal memory window, I can actually view the contents of my array. So I can actually take a look at source here, and I can pop it into here, and it will give me these values. I'll change it to 32 floating point, which is actually what we used, and that's the values that we actually loaded in there. So 42, 43, monotonically increasing there. So that's a good thing, and I could do that with the other memory address too. Great, so memory's good, so we can see the memory. Another thing that will be good or of interest is we can check out this guy right here. Now, I'm playing around a little bit with this, and it looks kind of fun. This is telling me which block index I have. If we start actually with warps, it'll actually tell me my warp index and my thread index inside of this, and it will tell me that I've hit this breakpoint. It also tells me which core I'm actually computing on, which is kind of cool too. So it gives you all of this information that's available to you there. So you can sort it either by blocks or warps or all sorts of other things that I think you can even do functions, but less interesting when there's only one function there. So that's good. And then we can also do the warp watch, which is interesting. So this one I like, because what you can do is you can pass in the variable name. So this is in a register. Now, it doesn't have any value yet, because we haven't obviously done that. So let's step. And it will tell me the value of index for this warp. If I want to switch to a different warp, I can go to the next active warp. And again, it breaks there. But then it will grab the next values. And again, we'll talk about a warp this afternoon, but just call it a group of 32 threads and for now. So, okay, so that's looking good. We can see all sorts of neat information there. We've also got a memory checker, which we'll play with as well. So I think the thing that I actually want to take a look at is, let's see what's going on here. How do I want to do this? Okay, so we want to find out where the error is and why this isn't working. So maybe let's see if we can go to the next active warp here. Maybe I'll just move my breakpoint. Okay, now this looks a little bit suspicious. So I've stepped over one a little bit. You can also hover over here. So thread index 0, block index is 1. But why is my thread index 16? Because the block size is actually 64. I would expect it to go from 0 to 63 and 64. And the issue that I actually have here is that I've actually done this calculation incorrectly. We shouldn't be using the grid dimension. We need to really be using the block dimension there. So we need the block dimension instead. And how did I know that? Because this is supposed to be 0, 32, 64, not 16. So something fishy was there. So that's the error in this code. Obviously a pretty trivial error. So I'll stop this. Now, if I were to do this again, it won't rebuild it. So I need to either do this or rebuild the solution to make sure that it captures the updated kernel. Okay. All right, so it's updated. We go to start CUDA debugging. Great, and if I go to the next couple warps, now it looks like I'm doing good. So, okay, so everything's good. So I'll stop this, and we'll just run it, and we'll get a raise match, and there won't be any more problems ever, right? Okay. There we go. So we notice right now that it's actually detecting an out-of-bounds access. Why did that occur? I had my memory check enabled, but it's occurring because I passed in size of 1,000, but I didn't do the comparison against n. So I'm actually overwriting out of bounds. So it actually picked up the memory access. You can enable it so that it'll continue to run through this, and it will display all the memory outputs at the end. It'll continue to report that there's a memory access violation. And there you go. You can actually see in the output window, if we scroll up, it detected 24 threads causing an access violation here. And it actually tells you quite nicely the block index and the thread index. And sure enough, if you take 16 times 15, let's pretend that's 960, plus 40 is 1,000. And then that means it's out of bounds. So, and it's out of bounds on line 18, which should be that guy right there, line 18. So it's telling you that you're writing out of bounds there. So it's picking up all those, and it's reporting quite nicely to us that we're writing out of bounds. So that's pretty nice, and that actually is quite helpful to avoid those issues. So let's correct that. I'll be lazy and just put it. We'll just check it here, and we'll put that there, and then see that that fixes it. So we'll build this. Make sure we're less than 1,000 before we try to access it. We use our start CUDA debugging. And no problems right there. And if we go to start without debugging, yay, our arrays match. Woohoo. Okay, so next thing I want to show you guys is how we can do a leak check, where we can check to see if there's any memory leaks here. So I'm going to go to the command prompt. I need to go to my desktop. Okay, so the first thing that we've also noticed too is if you don't build it in 64, at least for a 64-bit machine, the leak checking actually doesn't work. So that's something we need to watch out for as well. So we'll do that. And then we'll do, the other thing I want to do too is I'll show you how it does pick up the error here. So we'll rebuild this. Okay. cuda-memcheck, and we'll pass in the executable. So that's all you have to do is pass in the executable, and cuda-memcheck will determine that there's a bunch of errors. So again, if we compile it back in, we fix that, those errors are going to go away. And then we run it again, no more errors. All right, now you'll notice though, however, I didn't actually free my memory here. I didn't call CUDA free, so I'm actually leaking memory. So what we can do is we can actually pass in a leak check argument. Into this exercise. And it'll actually pick up that we're leaking memory. We didn't free those arrays. It'll actually report that. As again, a couple hints. You're going to need to make sure that it's in 64. You also need to call CUDA device reset, or else that won't be picked up also. So those are a couple things that we have there. And I think that's all I wanted to show you. Again, it wasn't intended to be like a demo of NSight, because there's some fantastic tools there that they do have. It's just stuff that we kind of use a little bit more from time to time on the memcheck. Sort of as the highlight, like things that, the toughest ones I have to admit that we've run into in the past, like just kind of sharing some stories with you. Driver issues have been really tough to debug. Like sometimes the driver every now and again will get an error. Now, granted, if you think it's a driver error, it's probably not. Like initially that's what we used to think it always was. Sometimes it was, but very rarely it actually ended up being. But the best thing to do there is distill it, and Nvidia does a great job of responding to driver error issues. You just post it to them through the proper channels, and they'll get that all fixed out. Those are good. And then otherwise, yeah, like multi-GPUs can be a little bit tricky to debug when you're exchanging information from GPU to GPU. Those ones are a little bit tough to sort out too. So Again, yeah, like I say, it's a little bit of a shorter lecture and demo, but give you guys some time to answer some questions and then get refreshed for the big profiling optimization one this afternoon. Cool. Any questions that you guys want to ask?